Hello and welcome to our first physics lab. This is going to be a lab on measurements and uncertainty, just to sort of get our feet wet with some of the instruments that we're going to be using in lab. Here in front of me I have a meter stick, a plastic ruler, a pair of Vernier calipers, and a double pan balance, also a meter tape. Now, this lab sort of focuses on just making measurements and doing some simple calculations, also doing some graphing. And so, let's talk about those measurements. Before you come to lab, you were to have read the sections linked right here on this web page to measurements and uncertainty, also error analysis, significant figures, and graphing with log or probe. So, let's take the meter stick for our first example. Now the meter stick, if you look at its smallest demarcations, the very smallest increment on the meter stick has a width of 1 millimeter. So these are 1 millimeter marks. And so when we make a measurement, let's say I'm going to try to maybe measure the diameter of this cup. And so let me go from 10, it looks like it has a diameter of 9.4 centimeters or 94 millimeters, just going to the least count of the instrument. Least count means the smallest demarcations. And if I just use the least count as a measure of my uncertainty, I can say that my uncertainty is plus or minus a millimeter. And so if I wanted to write that data point, it would look like this: 9.4 centimeters plus or minus 0.1 centimeters. And this would be my data point. This is how I would write it. Here's my uncertainty, and here is the actual measurement itself. And so as you can see, the uncertainty was determined by the least count. Now sometimes I can, if I'm really precise with this, I can do some estimating. So let's talk about estimating with the meter stick. I'll make that same measurement. It still looks like 9.4 centimeters, but maybe I can estimate to in between the smallest demarcations. Maybe to the nearest 1/2 of a millimeter. It looked like it was close to the halfway mark between 9.4 centimeters and 9.5 centimeters. And so I'd write that like this. I would say that's equal to 9.45 centimeters plus or minus 0.05 centimeters. Now that I'm estimating, my uncertainty has got a little smaller. It's going to the nearest half of a millimeter, or the nearest 0.05 centimeters. And so this is the same measurement, but this one is a little more precise because I'm estimating my uncertainty. And so as you can see here, the difference in these two measurements is the number of significant figures. This has 2, and this has 3, which you know by reading the resource on significant figures. Another thing to note about these measurements is that the uncertainty itself is to the same precision as the measurement. This is to the 10th place, this is to the 100th place, both the measurement and the uncertainty. So, when we're doing calculations that involve significant figures, those significant figures, if they're coming from data points that you measure, that measured uncertainty is what controls how many significant figures are in your data. And then that propagates throughout your calculations. Let's take a look at a couple of more measuring devices. The double pan balance is what you'll use to measure mass. And you put a mass on one side and move these sliding masses around until it balances. If the sliding masses aren't enough to balance this, then you can set an offset mass on the other side, but you'll have to add that mass into your total sum. So moving this around, it looks like this aluminum cylinder has a mass of about 70.04 grams. The smallest mark on this is 1/10 of a gram, or the nearest 0.1 grams. And so I would write that out then. This data point would be 70.4 grams plus or minus 0.1 grams. And so I've measured this weight, or this mass, to the nearest tenth of a gram. And again, I can go beyond that. This is 3 significant figures. I can estimate to the nearest halfway point and say that looks like it's actually 70.40. In other words, it's closer to 40 than it is to 45 or 35, 0.45 or 0.35 grams plus or minus 0.05 grams. So by estimating, I've increased my precision to the hundredths place, and now I have 4 significant figures. Now the last instrument I'll talk about is the Vernier calipers. Now Vernier calipers can be a pretty precise way of measuring widths. Okay. And we don't do any estimating with the Vernier calipers. I think this is small. I don't know if you can see how it works, but I do have this large set of Vernier calipers. And so let's say I'm going to measure something. Whoa. Okay, that's good enough. So as you can see here, I've opened the jaws of this to measure an item. And so this is 1 centimeter from 0 to 1 to 2 to 3 centimeters. Now, this mark here tells me how wide this is. So this is between 1.1 centimeter and 1.2 centimeters. So I get my last digit, this is 1.1 something. The way I get my last digit is I follow along the calipers and I find where one of these top lines lines up well with the bottom line. Looks like that one lines up the best. And so let's count over. 0, 1, 2, 3, 4, 5, 6. The 6th line lines up well with the line beneath it. And so that's my last decimal of precision. 1.16 centimeters. And this is plus or minus 0.01 centimeter using the huge Vernier caliper. And so I'd write it like this. 1.16 centimeters plus or minus 0.01 centimeters. And so by that I can get pretty good precision using Vernier calipers. It's usually much better than just using a meter stick or a plastic ruler. Another very interesting device for measuring distances is the micrometer. And here's what this looks like. And I'm going to measure the width of this aluminum block using the micrometer. Now you don't want to tighten using this larger knob because you can over tighten very easily. I'm going to tighten using this end pin, and when it gets to the width, it begins to ratchet, which lets me know that's as far as it'll go. I don't want to clamp it down by tightening here. I don't want to clamp it. I just want to get exactly there. This is like a little torque wrench. It won't let me over tighten. So now when I read this, there's a horizontal marking this way. It goes, the smallest mark, the least count, is a millimeter. And this says, okay, this is 13 millimeters. Now below the horizontal line are other markings which indicate half millimeters. And so as I look at this, it's past 13 millimeters, but it's not yet quite at 13 and a half, or else the other line would show up. So this is somewhere between 13 and 13.5 millimeters. Now, there are lines going around here in a circular way around this direction of the micrometer. And these are numbered 0 to 50. And the way this works is you take a look at what number lines up best with this horizontal line, and it looks like I'm right here between 23 and 24. And that tells me how many hundredths of a millimeter have elapsed. So this is 13.24 let's say it's closer to 13.23 actually. 13.23 millimeters. Now, if I'd already passed the halfway point, it would have been 13.5 plus 23, or 13.73 millimeters. But I hadn't crossed the halfway point between the 13th and 14th millimeter yet horizontally. And so I'll write that out, and it looks like this. This width is equal to 13.23 millimeters plus or minus 0.01 millimeters. 4 significant figures, which is great for a width measurement. But you can actually estimate beyond that. You can go maybe to the nearest half of a millimeter. It looks like it's closer to 13.23 than it is to the 23 than it is to 23.5 or 22.5. And so I could give it even more precision. 13.230 millimeters plus or minus a half of a hundredth of a millimeter. And right there I have a number with 5 significant digits for the width of that aluminum block, which is very precise. All right, so once you've made your measurements, you know the number of significant figures in each data point, you know what the uncertainty is, you've got the correct units down. Now you're able to make some calculations using that data and follow this uncertainty all the way through your calculations. This is called propagating your error. And you will calculate the density of a sample of aluminum this way, and when you do that, you're going to be required to propagate your error through your calculations. In order to do this, please refer to the resource online on this page that links to instructions on how to propagate errors in calculations. The second set of activities for this lab will be motion. And we have a motion sensor that will help us examine that. This motion sensor is attached to the computer, and you'll have to bring up a software on the computer called Logger Pro. What this motion sensor does is it sends out an ultrasonic signal. It acts as a speaker, and it sends out a sound pulse. And then it converts itself quickly to a microphone to receive the sound pulse back in after it reflects off of a nearby object. And so by knowing the amount of time elapsed between when it sent out the sound and when it received the sound back, and making an assumption about the velocity of sound in air, with that information of velocity and time, it can calculate the distance to the object and back. Cut that in half, you have the distance to the object. Now, it does this many times per second. And so if an object is moving, and it knows how much time elapses between each of the pulses that it sends, it can make determinations of how that object's position is changing with time, and therefore it can calculate that object's velocity. And so we'll be using this. You'll be examining several different types of motion with this motion detector, and making graphs of position versus time, and also velocity versus time. And we'll discover sort of an interesting thing about the slope of a position versus time graph and how it relates to velocity.